Actor-Critic Method. So this webinar is basically an overview of the lesson on Actor-Critic Method in your classroom. So this is where everything can be put together, the concepts that you have learned until now, um, including for TD methods, MC method, then value-based methods, policy-based methods, and then you implemented DQN and reinforce algorithms. And so in this lesson, we put them together and see how it can be utilized to make our the learning of our agent better, more efficient, faster, stable. Uh, so so let's get started. So first of all, let's review uh, some basics. So value-based methods. We just learned a few weeks ago. DQN was the one of the algorithms that utilizes value-based methods. So basically, value-based methods uh, is when an agent uses a deep neural network to approximate a value function, right? So these are the value functions, and once it approximates the value function, it can determine the policy. So just to remind you, V by S is the value function for deterministic policy. So value given state S, V star will be the optimal, the final optimal value function. Q pi SA is the action value function. So this is state value function V by S specifically, and this is the action value function, and it is for stochastic policy, right? And of course, Q star is the optimal action value function. A pi is the advantage function. You might not have, we didn't actually see much explanation on this, but it is also based on stochastic policy, and and it also depends on a state and action pair. Uh, and then, so an agent or an algorithm that uses value-based methods will first approximate this, and that means it will come up with a neural network that gives out one of these given the state or state and action, and and based on what the neural network outputs, uh, the the values that the neural network outputs of these, based on those values we figure out our policy. I mean, by policy, by of course I mean what action to take given a state, or by SA if it's a stochastic policy. So now let's take a look at the policy-based methods. As the name suggests, again, uh, policy-based methods directly uh, approximates the policy instead of going via the route of approximating a value function. It directly estimates a policy. So reinforce was the one of the example of the algorithms based on policy-based methods, and this is what you implemented uh, in past few weeks. And so it directly approximates or estimates the policies. It doesn't depend on estimating a value function. And I've also explained in the webinar based on policy-based methods what is the difference between value-based and policy-based methods. It is not just that one is computing value first and then policy, another directly goes to policy. It is not that superficial. It's there is some more in there, so I suggest you watch that webinar, because even if I'll just quickly overview that too. So because even if a, so given a value, an agent will select an action, right? And mostly this is uh, a greedy policy. If it's a deterministic policy, greedy, or it will sample one of those actions if it's a stochastic policy. And mostly the agent picks the action with highest value or the action which has highest probability, right? But here the agent might choose an action which has low uh, action value, but it is good in the long term to improve the total expected return. So that's why these networks directly approximate a policy, uh, looking at the total final expected return, and they might choose an action with low value in between, but overall uh, the agent or the neural network thinks that it will lead to a very high expected return. So that's the actual difference between value based and policy based methods. So this makes the policy-based method, an agent that uses policy-based method, uh, better in choosing action because uh, it thinks in the long term. It thinks of improving the total return from one single episode as well as a number of episodes. Uh, and that's what we want from our environment as well. If we are training an agent to solve an environment, we want to maximize its score. That's what we do when we implement this, and that's what matters. And to maximize score, it doesn't mean all the actions at each time step have to be the best actions. uh, an agent might choose a weaker action, but ultimately if it leads to higher score, then that action was a good thing. So that's why that makes policy based methods better for selecting actions given a state or a given a state action pair. So please keep this in mind. So actor critic method is basically an intersection of value based methods and policy based methods. uh, Actor critic, so these are two networks. One is called an actor, another is called critic. They are not identical networks. In DQN we saw them as identical, but in this case, in DQN algorithm they were identical, but in this case they might not necessarily be identical networks. The actor network uh, determines the actions given an input of state or state action pair. So as you might have guessed, this actor will be based on policy based method, and the critic method determines the value of taking that action. And so this critic network will be based on value based method. So actor critic method is just a combination of policy based method, value based method, where the actor follows policy based method, and the critic, the network that computes the value of a particular action, follows a value based method. Very straightforward, simple stuff. So reinforce, now we saw reinforce in policy based methods, right? So this is an example of why policy based method is a good an agent that follows a policy based method will be a good actor uh, here, because again, as I explained, that here the agent will look at the final outcome. So suppose this is the final score, and depending on that, it will either increase or decrease the probability of these actions. So again, to recap, uh, the agent first collects a number of episodes, and then it, and it is following a stochastic policy. And suppose during training you go back to training, and you say, okay, when I saw this state, I took left action because it had higher probability. And since I took this action, it turned out to be good for the agent in the end, and the agent agent won the the episode. That means this left policy is good given this state, given this state. So I should increase its probability even more and decrease the probability of others, because I don't want to risk uh, taking any other action given this state. Same the agent will do for other uh, outputs. Uh, it will increase the probability of the action that led to a good reward, and vice versa for a bad reward. And this is based on policy-based methods. So that's why uh, policy-based method can be a good actor. Now, what about the other network, the critic? Because the critic is the one that is going to rank or uh, decide how good that action was, right? Because now you're taking this, given this output, sorry, given this state, you take this action and you look at the final reward. But there has to be something that computes this as well. So in order to determine whether this action was good or not, should I increase its probability or not, I need to compute this. So for the computing the expected return given any state and any action, we use the critic network. And again, you might have guessed that the critic network is dependent on value-based method, because we are computing the value, the expected return of a given state and or given state action pair. So, so there are two ways of estimated returns, right? We learned there was one MC method, Monte Carlo method, and there was another TD method, temporal difference method. And one of those will be used uh, for our value-based method. One of those, or later on, you will see a combination of these. We'll talk about the combination later, but so let's see the pros and cons of MC method. Uh, when you in MC method, you have to, before computing any value given a state. So before computing the value of a state, you have to first uh, experience the whole episode, if it's an episodic task or a number of time steps for a continuing task. So you have to first experience a number of episodes, right? And then uh, you estimate the value given a particular state. But since we are going all the way until the end, uh, these returns might be very different from each other, because uh, there might be many random actions taking place in between, and because of these random actions taking place, so in the beginning they all start the same, right? But in between there might be random actions which are different from the other episodes, and which might be different from this episode, the random states that take place. Sorry, I said random actions, sorry, the random states that take place later on in the episode might be different, and that's why they might have high variance in their expected return, and that's why MC method has a very high variance. On the other hand, it has a low bias because it's not estimating anything, it's not guessing anything, uh, because we are going all the way until the end, right? So it has low bias but high variance. And on the other hand, TD method, we don't go all the end, for all the way until the end of the episode. We given one state at time step t, we just take one step and estimate the total expected return for the whole episode from this one time step, right? We don't go all the way until the end. That's why the random actions that might have taken place don't take place here, or we don't assume, or we don't even consider them. We just make a guess, and we assume that our another guess will also be closer to our current guess. It won't be that far from our current guess. So there is not much difference in our guesses. Again, I'm saying guesses because we are guessing the total expected return given this next state, right? So it's going to be reward for going in that state plus gamma times gt plus 1. Now gt plus 1, again, all you know, it's sum of all the cumulative, it's sum of all the rewards after that time step until the end. So we are guessing that the sum of all the rewards until the time end discounted here won't be much different for this episode, won't be much different for next episode, so they are all close to each other. So we get low variance, but it will have a high bias because again we are guessing uh, that there won't be much variance. We are guessing this expected return. So TD method has low variance but high bias, whereas MC method has high variance but low or zero bias, almost zero bias. So depending on our need, we need to use either MC method or TD method uh, to compute value for our critic. So we'll use one of these in our critic to compute the action value or state value function. Um, Now reinforce, again you can see the lesson and the webinar. I told you that there is very high variance in reinforce because reinforce goes all the way until the end. We have discussed this previously. It goes until the end. So uh, since it goes until the end, since it goes until the end, it has to follow. It's following MC method, Monte Carlo method. Reinforce algorithm is following Monte Carlo method. So it's expected return as well as um, the gradient that we compute has a high variance. It's very noisy, and this was also one of the disadvantages or the weak points that we discussed during the reinforced lesson, that its gradient is very noisy. And then the solution that we found for this was that we will uh, average the returns of our trajectories, or we will normalize the returns of n trajectories. uh, uh, and I encourage you to go and look up again in the lesson for reinforce. This is what we did. So that's what we did during the reinforce method. But uh, that also reduces the variance, but there could be even more done to reduce the variance of this reinforce algorithm, which is based on policy based methods. So and that solution is to use a another network that is based on TD method, right? So since the actor network is based on MC method, which has high variance, but it is computing right actions. So we will just use this network for estimating the actions, while we will use another network to compute or to estimate the value of each state action pair. And that network will be based on TD method, and that way we will reduce the variance overall of our agent, of our learning, and it will also result in a stable learning, and eh, stable and less there will be less variance. uh, Now there will be bias because we are guessing a lot of things, but there are some other ways of compensating for the bias, which we will discuss later on. So actor critic is use a fast learning policy based method as an actor. For example, reinforce. Reinforce is just one example of policy based method. Again, I want to emphasize that, and I'm just using reinforce as an example here. So use a fast learning policy based method as an actor, which estimates actions better, and use a TD method based critic to compute the action value or state value and reduce the variance. So we get the best of both the networks, best of both uh, concepts. And that's what actor critic algorithm is, or an agent based on actor critic method does. It uses one network for this purpose and other network for this purpose, and combines them, uh, and it's better learning and faster and stable learning. So let's look at a typical training process. This is not uh, a training process for all the algorithms based on actor-critic method, but this is like one of the ways, typical ways. So given a state S, let me, I will, so let me go here. Okay. So given, so there are two networks. One is an actor and another is a critic. Actor will generate a policy given a state, uh, and it might be a deterministic policy or a stochastic policy, and it can also be a continuous policy, which we'll see later. And a critic, given a state, computes the state value of that state. This could also be a state action pair. I could also input state action pair here if it's a stochastic policy, and then this becomes Q. Uh, so this becomes an action value function. So the overall basic underlying principle is that actor takes state, gives out policy, critic will generate the action or state value given a state or state action pair. So what is the process? So a state, so actor takes in state, gives out uh, an action, and this action then goes into the environment, and the environment gives out reward and next state. Now we need to compute the TD target, right? So let's come back to this slide. So the environment gave us next state and reward. Now we have to first compute the TD target such that we can compare the TD target with the actual uh, state value, and then train our networks. So in order to first generate a TD target, we need to compute the state value for next state, right? So that's what we'll do first. Now the environment, after inputting state and giving out action, action goes into environment, and the environment gives out uh, next state and reward. Now we use this next state. Now assume that this is S prime. So we use this S prime, input it to our critic network, and then critic network we give out V of S prime, and given this network, and then the V of S prime will be used to compute a TD target. So this is reward plus gamma times whatever the this network gives out, the V of S prime. Then we use this V of S prime here, and we compute, given S, we also compute our state function, state value function, and that gives us our advantage function. And then we use this advantage function to train our local, our actor network. So we are using two networks. One gives out action, other gives out state value. We first compute the next state's state value, compute. We first estimate the next state value, compute TD target, use the TD target to get advantage function, and then we use advantage function to train this actor network. So what are the different types of actor-critic networks, popular actor-critic networks? A3C has also uh, known as asynchronous advantage actor-critic, 3As and 3C. So the asynchronous part is that so there are many agents, and each agent has its own copy of this network, uh, and it has its own copy of the environment. Now this network here, I have shown only one network, and the point of showing this is that this network has two heads, one for actor and one for critic, and they share their parameters, and they train at the same time, the actor and critic. But it's this one network could also be two networks, one separately for actor and one separately for critic. Okay, so what happens is there are many agents, and they have their own local copy of current version of actor and critic network. Now using the actor network and the environment, they collect these experiences. You might remember this from replay buffer. So they are collecting these experiences, and then they use these experiences to update their own local version of the critic network, right? Then they use that critic network and then update the global network, right? So that's done by one agent. It uses, first of all, it uses so its own copy of actor and critic network, generates this, updates critic network, and then it just updates the one single global network. And this is done by all these agents, and they are all doing this asynchronously. That is, they are not correlated, they are just doing it randomly. Collect, update, and then update this, collect, update their local, and then update the global. There is only one copy of actor global actor network and one copy of global local network, but each agent has their own copy of local actor critic networks, and using those they are generating this, updating their critic, and then dumping it on their global networks, and they are doing this all at the same time. That's why this is called asynchronous, and the point of being asynchronous is to avoid any correlation, right? So the if you remember replay buffer from the DQN method, we first collected a lot of experiences and then trained the network in mini batches, right? So the point of the collecting all these experiences uh, and not collecting one single experience and then stacking them together was to avoid any correlation. Again, more details in the DQN webinar. So to reduce the correlation, right? But this was done off policy, right? So first we collected everything down, put them in a buffer, and then we sampled batches from the buffer and then trained the network. uh, Asynchronous network does the same thing, but it does on policy. So I will discuss what on policy and off policy is soon. So on policy is when you use the uh, same policy to select action as well as update your network. So SARSA was an on policy method. On policy we had epsilon greedy policy, and we using the epsilon greedy policy we said, okay, given this state and action, I will select, I will get next state from the environment, and then I will select this action a prime. That's what I got from our my epsilon greedy policy. And I used a prime to compute q s prime a prime, update my QSA using this. Again, this is the TD target, this is TD error, remember. So I use S prime A prime to, for this purpose, for updating my action value function. But I also took the same action when I came to, when I entered S prime. So my policy of updating action value function, my policy of selecting my A prime for updating action value, as well as for taking my action was the same. Okay, that's called on policy. But when it comes to off policy, you select an action to update your action value, but you might not necessarily take the same action. That's called off policy. You might not take this action given this next state is prime. You just chose this action, and which is based on argmax greedy policy. So you chose this action just to update your action value, but you you use epsilon greedy policy to take an actual action. So uh, in summary, uh, sarsa or even expected sarsa, they use epsilon greedy policy to update as well as take the actual action, whereas Q learning or SARSA Max uses greedy policy to update action value, whereas it actually selects action A based on epsilon greedy policy. And since it's an epsilon greedy policy, it could be the same action or it might be some other actions, but there is no guarantee. So that's why this is called off policy, because there are two different off policy update, because it's updating with a different policy than actual action taking policy, and whereas this is called on policy. So going back to this, A3C is on policy, whereas when we use replay buffer, so this synchronous all different agents doing all the things together is on policy, whereas replay using replay buffer is off policy. And it's said that on policy is more uh, and it doesn't collapse after some point, or it does it, and it has more consistent convergence, but it's inefficient in use of experiences because you're not storing those experiences, right? So if you go back to this, they, each agent experiences all this, and it's going to dump all these experiences and collect new experiences, and it's done by all the agents. So it's inefficient in using the resources, but it's going to create a very stable and very stable network, and it and more consistent convergence. Whereas off policy is better use of resources because you are not throwing away the experiences, but it's going to have unstable and high variance. If you want more information on policy versus off policy, please check out this paper by Gu et al. Um, so it's a really good information, really good explanation in that paper. All right. So and so and say bootstrapping. So previously, when I talked about differences in TD and MC method. Sorry for doing all this back and forth, but I apologize for that. But it's important. So uh, I said that it has high variance but low bias, whereas TD method has low variance but high bias. And I said that in the future we will figure out a way to uh, compensate for that high bias. So one of those ways is end step bootstrapping. So in your critic network, instead of just computing v pi st plus 1, in some algorithms you see uh, some networks computing uh, v pi for more steps, so they don't rely on just one step. They will compute go for two steps or three steps or some end steps. That's why it's called end step bootstrapping. So in this version, so in end step bootstrapping, it's going to be either one step and then guessing until the end, or one two steps and then guessing until the end, or so it's going to be either one of these. um, and it's called end step bootstrapping because n could be one or until the end. To And this is done to deal with the bias. In the future, in this slide, I will show another way, which is even better, which is a combination actually of which is a modification to end step bootstrapping. So we already discussed this. Uh, Another popular uh, actor critic based algorithm is advantage actor critic. As you can see, it is very similar to the A3C, but again, the only thing missing here is the asynchronicity. And so, yeah, so it's not an asynchronous updating of the global copies of the actor critic networks, but everything is the same. But what the agent do before updating the local and so sorry the global actor and critic network is that they everyone waits until all agents have accumulated experiences and updated their networks, and they all wait and then they update everything together. So so it's a synchronized updating. That's why it doesn't have that asynchronous element here. Yeah, so that's the advantage over A3C is that this is, excuse me, uh, in this method, uh, you are you can use a CPU because not much parallel updating is taking place, whereas in A3C you need a GPU. So in A3C you need a GPU. For A2C you can use a CPU, right? So as I said, the modification to end-step bootstrapping is generalized advantage estimation, and you might have seen this in the lesson as well. So this is a very smart way of reducing the bias in the critic, and at the same time you can keep the variance low because you're using a TD method, right? So TD method helps keep the variance low, but it has high bias, so you figure out something to reduce that bias and compensate for that bias for using TD method. So for GAE, basically what it is this GT is an expected return, and this GT is different in each case. So GT here is only for one step. GT here is going for two steps and then guessing until the end. So two-step bootstrapping. Here it's for going three steps and then guessing, going four steps and then guessing. And this might be all the way until the end. Yeah. So for each uh, type of uh, bootstrapping, you compute individual expected return, one step for two steps separate, and then you combine all them. You take a weighted average of all them and put them together. And depending on your uh, preference or use, you select how many steps you want to go. So you select how many steps should be used to take the average, how many GTs you want to use to take the average. So depending on how many steps you use, it's going to be either very low bias or just like a TD method. So let's take a look at the equation here. So 1 minus lambda, and then this is 1 minus lambda times lambda. So these are the multipliers for each of these individual expected return from each case. 1 minus lambda times lambda. So this is second step. Third step is lambda square, lambda n, and so on. And then you multiply them each. Suppose you chose the lambda as 0.5. So you compute this 1 minus lambda, 1 minus lambda times lambda, and multiply them by each of them, and then take a sum. So it's like you are taking their weights. You decide the weights for each of them, and then you sum up the weights time the the expected returns. And depending on your preference, you if you say, okay, my n is 0, so that means this becomes 1 minus lambda. That means you just use first step. Where right, so you can decide your n, as well as you can decide the value of your lambda, how much emphasis you want to give to each expected return, how fast you want the return, the weights of the multiplying weights of the returns to diminish, right? If you use a very high number, uh, so it's going to be zero point 0.1 times 0.9, 0.09. So depending on that, it will either decrease fast or increase fast. So just like gamma, right? You use gamma to decide how much emphasis to give to future rewards. This is for end step bootstrapping, and this allows you to take into account uh, many steps, right? So it helps reduce the bias, and already you are reducing the variance. So and if you used all these uh, all these returns equally and then took average, right? It would have uh, worked against your need of reducing variance, because if you take it becomes, if you take average, then it would have increased the variance. But this way, the variance will slightly increase, but not as much, because you are weighing them, and your weights are reducing as you go further and further in time, depending on your lambda. So depending on your lambda, you can decide how how much the bias will be reduced and how much the variance will be increased because of using end step bootstrapping, right? So there is also a paper on this, and it's mentioned in the lesson, so please take a look at that. And even you can implement this in your project if necessary, and see for yourself how it improves your algorithm. Right, now deep deterministic policy gradient. So we discussed these networks for deterministic policy as well as for stochastic policy, but what about for continuous action spaces? So for that, there is this DDPG algorithm, uh, and you will be implementing this for your project as well. So in this, uh, there is a the actor network will give out uh, set of actions, and all actions uh, pertain to uh, your continuous action space, right? Because in this case, your environment has continuous action space. So the actions are going to lie in a range. So what the network gives out uh, is going to be believed as the best action ever, right? There is not going to be a stochastic policy like a distribution of actions. It's going to be just one action given out, and it's going to be believed as the best action, right? So it's also said to be as a DTPG is also said to be as a DQN for continuous action spaces, right? In DQN you use argmax. Here you don't use argmax, but this also gives out just one set of numbers for the your continuous action space, and this uses again actor-critic method. So let's take a look at how it works. So there are two copies of each network. So there is a actor local and actor target, the critic local and critic target, and uh, the action that the actor network will give out is going to be continuous. So it's not a pie or a distribution or a policy. It's just one, you know, one set of one action or one set of numbers for your continuous action space. So suppose there is a continuous action space of four parameters. There will be four numbers given out, and it's believed that that is the best given this state. So let's take a look how this works, and this will also help you, this general overflow of DDPG, help you understand the code in this lesson, uh, as well as the code for your um, project for multi-agent DDPG as well. Okay, so first of all, given a state, actor local will generate an action here. That action goes to the environment and it gives out reward and next state. Then you will use this next state, and you will use another network called actor target to compute another action. Now here the difference between this and the one we discussed previously is that here there is a state action. State and action both are involved as compared to just the state. That's why we need to use another set of networks, right? So given a state, you get an action, you get reward and S prime from the environment. Now you need to choose what action you will select given S prime as well, because because you have to compute an action value here as opposed to state value we previously saw. So to choose that action, you need actor target. You input your S prime to actor target. It gives out A prime that you will take given S prime. You use S prime A prime, input it to the critic target. Now remember, previously we just inputted S. Here we are inputting S prime and A prime both to compute an action value. Now I have written it's at V, but it's actually Q, but I'm calling it as the action value of the state action pair. So that way it's clear. So I will input this and it will give me an action value for the next state and next action pair. Now I will take this and compute my TD target. Remember, every time we are computing TD target based on next state or next state and action pair, right? And if you are using end state bootstrapping, this will be multiple next states. Okay, depending on you, you should experiment with that. So we got this, and based on this, we compute this. We use R from here, and whatever the critic target gave out, we use the action value here, and we compute the TD target. Now we need to compute the root mean squared loss between our TD target, the ideal, and our action value. Now over here I have written S, but it should be actually S and A. So let me see if I can correct it. First of all, here it's going to be A prime, S prime, and here it's going to be A. Here also it's going to be A, and these are Q's. So sorry about that. I'll just make this as Q. That Q. So okay, so going back, so let's go back a few steps. So we computed this TD target. We computed this TD target, and we will use our the state and the action here to compute QSA. QSA first. The action value give based on our current version of critic local network. So remember that here we want to train our local actor and local critic networks. These are the ones we will be using to solve our environment, or these are going to be our, the combination of these two are going to be our agent. So we are concerned about training this and this. Okay, we don't train this, we will just soft update this later, but we are actually training these two networks. These will be used combined as an agent. So we computed TD target here. Okay, we went through this, and then we computed TD target. Then we used our S and A and the current version of our critic local network. I'm saying current version because we are going to update this. So we will use current version of our critic local network to compute this action value given state A, and we will compute root mean square loss between our TD target and this this network. Sorry, this action value. We use this root mean square loss and backpropagation to update our critic local network such that we want to reduce this loss. So we update our critic local network in order to reduce the loss between our TD target and the action value generated by our current version of local network. We update that network, and that updated network then generate so the new QSA. This Q. Okay. So again, few steps back. TD target, current version of critic local gave out will give out an action value. We use backpropagation to reduce the RMS loss between TD target and this, and then update our critic local. We use the updated critic local to generate new action value given again state S and A. So this should be different than this because we have updated our network to match this to our TD target. So we get this new updated action value given S and A. We use this updated action value to update our actor local network such that uh, we we update our actor local network such that it reduces uh, minus of QSA. That means it it maximizes the action value. So we update or train our local actor network such that it will maximize this new updated value of the action value of state action pair SA. So that's the process of updating our actor and critic local network. is that we first update this critic local and then use that to update our actor local such that it maximizes the action value given out by the updated critic local network. So I'm repeating a lot, but sorry about that. But I just want to make this flow clear because you will have to use this code in your projects. So I just want to make this flow clear. Thank you. So yeah, so that's it for this webinar. Please go through the code, the DDBG code in this lesson, and I hope the explanation I gave today helps you finish your project. And if you have any questions, feel free to ask me anytime on Slack. So thanks. That is it from my side, and have a good one. Thank you.